From the last lecture, we can see that the motor speed or the torque for a DC brushed motor will be a function of following parameters: the terminal voltage applied to the armature winding, the armature resistance, because that affects how much current it produces from the certain terminal voltage, but it also depends on the field flux as well. Okay, the magnetic field produced by the field winding. All of that can be used to control electromotors. Sometimes in the olden days, when we didn't have the good power electronics, people used variable resistors connected in series with armature winding to reduce the current or to control the current for certain voltage or for fixed voltage. But that, of course, increases losses unnecessarily. If you don't use a magnetic field and have field windings instead, then you can actually also control the current of the field. That would in turn affect the torque and the speed. So there are various ways of doing control, but nowadays, because now we can actually control the voltage a lot easier than we used to be able to with electronics. Okay, remember the DC, for example, the DC-DC converters or buck converters or DC to AC inverters we have nowadays. We can actually control the voltage, control the frequency of the voltage fairly easily. Therefore, that will give us a lot more flexibility to control this kind of motors. But motors, like all other things, comes with losses. So efficiency of the motors will be something that people will have to consider very carefully. Now, if you think about the definition or the concept of efficiency, it's basically the output power over input power. That's it's fairly universal. It can apply to any system or subsystems. It's the total output over input. That's the level of efficiency. But for electrical motors, there are different types of losses associated that compromise the efficiency. Now I'm listed here at the bottom of my slide, or this slide, says the copper losses, the iron losses, the friction and the windage losses, and the constant losses. Now this is not just for the brushed DC motors, although, obviously different types of motors will have different level of losses for each of these items. But in general, all electric motors will have all 4 different kinds of losses in a machine. Just that the level can be quite different. Copper losses are related to the electrical resistances in the windings, in particular the armature winding, because the armature current is quite high, the resistance is low, and the power equals to I square R. Okay, so it goes up proportional to the square of the current, as indicated in equation number 1. But also because current torque relationship, the torque is proportional to the armature current as well. Therefore, you can actually consider the copper loss proportional to the output torque of the motor. Okay, so that's how you can actually estimate the torque, the power loss due to the current what we call the copper losses, because windings typically use copper for the winding materials. Sometimes people can use other windings like aluminium type of windings, but again, we don't call it aluminium just because the copper are more commonly used. We call them copper losses, as to basically they are losses due to currents. Then there are iron losses. But iron losses is caused by magnetic field, something called Hall effect. Magnetic field going through the ions in the rotor. Typically in the stator or the rotor, and it is proportional to the frequency of the magnetic field change, or really the speed of the rotation of the rotor. Okay, it has a lot to do with the magnetic field rather than current. Okay, and it can be quite high. Depends on how the rotor and the stator are structured with the iron materials. Okay, typically they are laminated slices to reduce the iron losses, but it was, it can only help to reduce it, but it won't be able to eliminate the losses altogether. Okay, so as long as you use iron materials for the bulk part of your structure, which is sort of fairly commonly used because the strength and also because the need to direct the flux to flow in certain ways, so you need the iron in there, but the effect is that it comes with prices in the iron losses. So for those of you, or for people on this program, and all you need to know is that it's actually related to the iron material in electrolyte. We don't really get into the electromagnetic field side of things too much. Then there's the friction and the windage losses, which are easier for us to understand. There are frictions between the brushes and the commutators. Then there are frictions of the bearings. You have a rotating part; it needs to be fixed with bearings, so that causes losses, which is the friction losses tend to be sort of approximately proportional to the rotational speed. And they have windages. It's a bit like a sort of aerodynamic air drag of a vehicle. That power loss is sort of to the square of the speed, because the air drag, remember, is proportional to the square, and then force times speed that give you power. So that's really related to the power. The power is related to the cube of the rotational speed. Again, the level of these losses depend on the actual design of the motor. And then there are losses that's not really dependent on speed. As well, there are things like in the control circuits for controlling the motors, and also the current that needed to supply the field winding. The field winding is not rotating. Okay, it has nothing to do with the speed. So they don't change with speed, and they are constant values. Okay, so all sorts of losses in a machine that needs to be considered. Sometimes you are given the losses, sometimes you're probably given the parameters to calculate losses. But overall, the overall efficiency of the motor equals to the power output over power input. Power output is a torque produced by a motor times the rotational speed of the motor. That's mechanical power. Power input is V times I. The total VI for the armature winding, if you use the field winding as well, then plus the voltage of the field winding for the field winding and the current in the field winding as well. Okay, so that's one way to do it. If you know the operating conditions, you know the voltage and the current on an armature winding, and you also know the voltage and the current of the field winding, then you just substitute this into there, say put the mechanical power on the top and the total electrical power at the bottom. Now, if you are given particular values, specific parameters for different, the copper loss, the iron loss, and the friction loss, the windage loss, and the constant loss. If you can calculate all of that loss, then you can use output over P output plus the total losses to calculate the overall efficiency. That will be given in equation number 4. Okay, it just depends how, what you know, because you can only use what you know to work out what you want to find out. Okay, so that's about the losses. And I've set a couple, I think it's just only 2 questions, fairly simple questions for you for the calculation. One is about the current force and current torque force and and the speed, that kind of relationship. The other one is more about the efficiency, but you are given the particular losses there, so it's fairly easy to work out the overall efficiency. Okay, so fairly straightforward calculations. But before we what time I'm doing? Okay, so I'm just going to carry on and talk about the brushless DC motor and also the permanent magnet AC motor briefly. Now, brushless DC works very similar to the brushed DC motor, except it turns the motor rotor all the way around. So the magnetic field or the permanent magnet goes to the rotor, whereas the armature becomes the stator. Okay, so it works in the opposite way. And if you look at this one, I'm not really even going to use a motor, I'm just going to use a pair of magnets to represent this. Okay, so this, on this diagram here, this is the rotor. And that typically will be a pair of a permanent magnet. Okay, so we're going to use a permanent magnet that will have a north and south pole. On the stator, we'll have a coil that will also produce the magnetic field, a north and a south. Okay, now because when you have 2 magnets, north on one magnet will be attracted to the south of the other magnet, or the south of the first magnet will be attracted to the north of the other magnet. Therefore, that causes this rotor to rotate. Okay. Now, once this south gets to here, like the one you have here, and north gets to there, I can switch that off. Okay. Therefore, there's no magnetic field. Therefore, there's no forces there. But the motor will still rotate because of inertia. So once it starts to rotate away, then I'm going to swap them around. I'm going to make this side to south, this side to north. Now south pushes south away. So say this one is actually moved a little bit away. Now if I produce a south here, this source will push that source further away. This north will push this north further away until it goes back to there. Then north will attract to the north, and south will attract to north, will pull the magnet back around. Okay, so the operation of a brushless DC motor is even easier to understand from that point of view. You basically use a switchable magnet where you can switch around south and north pole with a rotor where you have a permanent magnet that have a fixed north and south pole. Okay, but I can change the polarity of the magnet on the stator to produce a rotating torque. Okay, because I can change the switch. This is just my switches here. I can change the direction of the current in the field. Therefore, I can change the magnet directions. Okay, I can switch it on and switch it off where I want to. And in reality, on a DC brushless motor, we have more than one pair of armature windings. So the armature winding typically will have 3 sets of controllable magnets on the stator, but with 1 pair of magnet on the rotor. Of course, we have number of poles, but that's slightly different matter. Okay, we have number of poles, and we can have several. That makes it better, the operation better. But to illustrate the point how we generate the force, and this diagram shows, give you a much better illustration how a brushless DC motor works. So over there, 1 pair. Let me find my mouse. So we have 1 pair here. This is A, this is B, A and A. This is B and B. This is C and C. So when the magnet is under here, it's directly under here. I'm actually going to switch that off because I don't want to produce anything. I'm going to produce a pole here, a south here to move this forward there, and I'm going to produce a north here to move that to there. Once the magnet is aligned with B and B, then I'm going to switch that off. Okay, I'm going to switch the other 2 on. So this one will have a north, pull that over. This side will have a south, pull that over. And then next time we'll have the face A again. When this lines with C and C, then we switch on the A phases. Okay, so you can see the forces that generated in there because we have 3 different phases, and it can be kind of continuous. That's brushless, the principle of brushless DC motor. How they work, it's fairly straightforward. Now, the other motor we have is permanent magnet ones, AC machine, but so I'm going to talk about that as well as I'm on this slide. Now, the permanent magnet machine has a very similar structure to the brushless DC motor, except the 3-phase currents. They are not really simply on and off. Okay, they are controlled in a pure sine wave or close to pure sine wave, depending on the rotational speed of the motor, to produce much smoother torque output. Okay, so structurally, if you look at the basic components of between the brushless DC motor and permanent magnet AC motor, structurally they're very similar, except the permanent magnet AC motor tends to be much larger in size. They give you better performance as well. Okay, that's why I said before in my lectures, the beginning of my lectures on this topic, I said, well, brushless DC is not really brushless. It's not really DC. It really works like an AC machine. Okay. Some simple comparisons and performances as well. Now, like a DC brushed motor, the current produced in the armature winding now installed on the stator is limited by the back EMF because the interaction between the magnetic field produced by the magnets on the stator and the armature winding. So the equivalent circuit that we had before that involved the back EMF also works. So back EMF is there to reduce the effect of the applied voltage and therefore reduces the current, and which in turn reduces the torque. So the torque produced in a brushless DC motor is affected by the back EMF as well. But performance-wise or behavior-wise, this motor works in a very similar fashion to a brushed DC motor, except that we don't have commutators, we don't have brushes, which make this type of motor a lot more attractive because of the improved reliability and reduced maintenance requirement. And this slide just compares the key differences between the two types of DC motor, brushed or brushless. Brushed motors have, because they have the brushes and commutators, they causes frictions and they causes electric arcing. It flashes of lights basically that tend to cause damage to the brushes and commutators. In a brushless motor, the windings are now on the stator. On the rotor, we have permanent magnet. And therefore, because the rotor, the winding is on the stator, they're not moving. Therefore, it's difficult for heat to dissipate. So you probably will need to consider some kind of cooling for the windings, because there's no wind. So therefore, there's no flow of air. It doesn't take the heat away. But overall, the brushless motor are a lot more reliable and more powerful as well than compared to the brushed motor. Okay, but they are more expensive because now we need a very strong permanent magnets, like rare earth type of magnets, to produce performance that are acceptable. I've already covered that earlier, so I'm not going to cover that anymore. So in my very last one, I will talk about the induction motors in my next lecture.